Good morning, good evening, good afternoon, wherever you are in the world today. And thank you for joining us for this AMETEK Solid-State Controls Understanding UPS Designs webinar. As always, before we get started, if you look on the right-hand side of your screen, you will see a chat bar. And if you don't mind, if you can hear my voice, please let me know in the chat bar that you can. And I actually tested this last week because strangely, I thought the webinar was last week and I started at 10 o'clock and nobody replied. So it just means the chat function does work. And I was speaking to myself for a considerable amount of time. So please type in the chat bar. Thank you, Andrew Nee. I appreciate that you can hear me. So I'm not speaking to myself this week, which is always very, very good. Okay, so today we'll go through the introductions while everybody else joins. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, and I'm based out of the Stafford, Texas facility, which is just south of Houston. I have over 20 years in the industrial UPS industry. I've worked with all the major manufacturers of UPSs in my prior lives, and now I've been with AMETEK Solid-State Controls for 8 years. There will be a lag of around about 15 to 30 seconds between when I talk and when you hear my voice. So that kind of makes things difficult when people type in questions when I'm speaking, because I'll only see the questions about 15 to 30 seconds after I've said something. So what I do ask people to do is if they go into the chat bar, there are two tabs on the chat bar. One is for chat and the other one says Q&A only. So if you can click on the Q&A only tab, if you have a question, type it in there. And then when I get to the end of the presentation, then I will go through all the questions and answers at the end, because it's just very difficult when I'm in the flow of what I'm talking about to field one of those questions as I go along. The platform that we use is called Webinar Jam. That's the webinar platform that we use, and it has a panic button. So that means if I'm talking and something goes wrong, if I see in the chat bar that people can't hear my voice or that the video is bad, that something is not quite going the way that it should, then I can press the panic button, and that takes us to a brand new room and cancels this room, and we carry on as if we had not had any issues, allegedly. So that's the way that it is supposed to work. And then another question that we get asked all the time is, will the webinar be recorded? And the webinar is recorded by Webinar Jam. And if you signed up for the webinar, you will get a link after the webinar has finished to rewatch the webinar. And the format that they put that webinar in, the video, it's not very easy to use. Basically, they just treat it as a new webinar. You press play and you've got to watch it all the way through. You can't rewind, fast forward, go to a certain point in the presentation. So what our fantastic marketing department do is they convert that into an MP4 and then they upload it to our YouTube channel. And the marketing department, as always, London is on the ball, and she has put a link in the chat to our YouTube channel. It usually takes 24 hours for all the new videos to get there, but every single webinar we have ever done is on our YouTube channel, and you can share it. You can send it to people. You can pause, rewind, fast forward, do whatever you need to do to get the best out of those presentations. And the last thing is the presentation should last round about 1 hour, with the caveat that that depends on how much I talk. So we'll see how it goes today. So the learning outcomes today are going to be, we're going to teach you to understand the major UPS topologies, understand the blocks of different UPS systems, the charger, the inverter, static switch, and all those kind of things. Discuss the advantages and disadvantages of the different topologies you can use when installing a UPS, and discuss the power flow power flow and general operation of each of the different topologies. Okay, so that's what we're going to focus on today. But we do have to get rid of a few of the common terms that we use so you understand what we're talking about. So when we say normal source AC input, that is the grid power that goes into the UPS that supplies power to the charger section of the UPS. Okay, battery charger and rectifier, that's self-explanatory. That converts normal source AC to DC and charges the batteries. Also supplies power to the inverter. The batteries obviously provide backup power during a normal loss of power, during a loss of normal source power. The inverter converts the DC back to AC and provides power to the critical loads that are being backed up by the UPS itself. The bypass source, which is also called auxiliary power source, or maybe even the reserve supply, that is a backup supply of AC power that we use if everything in the UPS itself has failed. We want to have another source of power for redundancy or to do maintenance if possible. The static transfer switch, that is an automatic switch that connects the load to inverter or the load to bypass. And it is a switch that has no moving parts. It actually uses SCRs, which are silicon controlled rectifiers. They're semiconductor devices. You send a signal to them and they turn on instantaneously with no moving parts in them. So they're very robust and very reliable. And then the last term that we're going to discuss is the remote bypass switch, or a bypass switch, which is a make before break mechanical switch that removes power from the UPS cabinet to allow safe maintenance procedures. It's always a physical switch, or it could even be a breaker arrangement. You can have maybe a 3-breaker arrangement, or sometimes I've seen a 5-breaker arrangement where you have to open and close the breakers in a certain way to bypass the UPS cubicle itself and to make it power free for maintenance. So here's a block diagram of a commercial UPS. Okay, and what you'll find is for a commercial UPS, these are not the UPSs that AMETEK Solidstate Controls makes, but they are out there and they are used sometimes in the industrial world. And you can see we have our AC input here, which is usually 480 volts AC. And then they call this CB1. This is actually a contactor in this UPS. And then that goes into a converter charger. So this is converting AC on the left to DC on the right, but it does it a little bit different from a normal industrial UPS system. What they have is they have a charger that trickle charges the battery, and there's also a DC to DC converter inside this section here. Okay, and then it also has a diode bridge. So this charger isn't a control bridge. It would just have 6 diodes, and it will convert whatever that 480 volts going in into DC, which usually works out to about 600 volts DC. Okay, it doesn't change. That's just the DC that goes into the inverter, and the batteries are usually charged at a nominal 480 volts for this system. So the DC bus is very high in this system. Okay, and then that DC goes into the inverter. The inverter converts that DC into AC, and then on the output we have this contact here, and it's a contactor. Okay, and in normal operation it's normally closed, and power will flow out that way there. And then on the static transfer switch, we have a contactor here as well, and then a circuit breaker here. So if the system fails, or the inverter output fails, what happens is the static transfer switch will immediately take this 480 volts out through the static switch and out to the output. But the static transfer switch is only rated to do that for a very small period of time. And what it does is, as soon as it sees that the static transfer switch which is the SCRs that have no moving parts. Once that has transferred the load, it will then pull in contactor 52S, and it will allow the power to flow through that way there, and then this transfer switch turns off. Okay, so the contactor is designed to keep power, 100% rating of the power going to the load circuits. The static transfer switch in commercial UPS does not. Okay. So remember, these are contactors. This is actually a circuit breaker. I shouldn't have labeled that as a contactor. They are circuit breakers in this system here. Okay. But the important thing to remember is there's no isolation transformer here in a commercial UPS and no isolation transformer there. And that's important because that gives you galvanic isolation. It gives you isolation between the two power sources. And if you don't have those isolation transformers, then the DC inside here has a reference to ground. So in some circumstances, depending on the design of the commercial UPS, if you go and work on this battery here and you measured between the positive terminal and ground, you may actually find that there is actually AC that is getting through the charger. And it could be as high if the charger is phased fully on. It could, in theory, be as high as 400 volts, 480 volts AC to ground if it's fully on. But in some circumstances, because the SCRs aren't going to be fully on, or the diodes aren't going to be fully on, it may be about 200 volts, but it is going to be AC, and it is an electric shock hazard if you don't have an isolation transformer here. Okay. And also what you find is the isolation that an isolation transformer gives you is if there is a failure in the battery charger, then it prevents the DC going back onto the AC at the distribution center, or the MCC that feeds the AC into the system. And that's a very bad thing if you get DC feeding back onto your AC supply. So if you know anything about transformers, you know that transformers cannot pass DC. So an isolation transformer gives you isolation between the charger and the AC input. And that is also the same if you have a transformer there. The inverter output, if there is some kind of failure in here and DC could somehow feed through that way there, the transformer would stop it. And it also helps with noise suppression as well. Okay, so as you can see here, we have the red power flow. That is the normal power flow, and the green is energized and ready. So in a commercial UPS, power flows from the AC input through the CB1 input breaker into the charger. The charger trickle charges the battery, and then the DC goes all the way through the inverter, through 52C contactor, and out to your critical loads. Okay. Oh, not enough room for me to write in there. And then our bypass supply is ready at this contactor here, and it's ready at the static switch, but we haven't turned it on. It's just waiting just in case the output of the inverter fails, and then it's ready to supply power. So in a commercial UPS, if you have an AC input failure, if the power fails, then the charger switches off. But it's just like you unplugging the plug from your laptop battery. Your laptop still carries on without any issues whatsoever. It doesn't switch to battery. What it does is the battery just takes over as the DC from the charger collapses, and maintains the DC into the inverter. So the power flow is now from the battery through the inverter and out to the output. Now, once again, in a commercial UPS, remember, there's a DC to DC converter inside that system. So it's taking this 480 volts and it's actually increasing it to about 600 volts going into the inverter. And that's electronic. And in some circumstances, electronics are the first things that fail over time. So it is it does introduce a mode of failure there with that DC to DC converter. And then if the batteries get to their end of life and the battery depletes and the AC doesn't come back on again, then the static transfer switch will turn on and will put the power to the load that way. And then instantaneously, it will then pull in contactor 52S and it will power the load through that contactor and the static switch will turn off. That is how the commercial UPS works when power fails. Now, this is a double conversion industrial UPS, and this is actually one of the block diagrams for an AMETEK solid-state controls UPS. And one important difference that you can see here is that our AC input is still 480 volts AC, but for this system here, we have 120 volts AC out, so therefore our bypass source is always going to match the AC output. So whatever the AC output is, that is what the bypass source AC input is going to be. So you can see in this circumstance, the 120 volts matches. And the important thing to remember as well is we do have the isolation transformers. So that gives us isolation here. It stops DC feeding back onto AC, and it gives us safety when we're working on these batteries, because now there is absolutely no AC reference from the positive of the battery to ground because of that isolation transformer. So you are safe to take readings on the batteries. There is no electric shock risk. Okay. And the normal power flow, once again, the red is the normal power flow and green is energized and ready. So once again, the AC input goes into the battery charger rectifier. And we don't have a DC to DC converter in here. We're just taking the AC and turning it into DC. Now, this battery is 60 cells lead acid. So it is going to be charged at 135 volts DC, roughly at 77 degrees Fahrenheit, which is 25 degrees C. Okay? That is for a 60 cell lead acid battery. That is what we are float charging the battery at. And then that DC also goes into the inverter, directly into the inverter, not through a DC to DC converter. And then that inverter changes the DC back into AC. That goes through an isolation transformer and then into our static switch. So remember on the previous commercial UPS, that was a contactor. In this system, we have two static switches. So this static switch is always on in normal operation, and then the power flows out to the AC output to the loads. Okay. And once again, our bypass is present at the bypass static switch, but the bypass static switch is not on. It's just waiting for a signal just in case the input to this static switch fails. And if we have a power failure on this, just like your laptop, the battery takes over seamlessly. It doesn't switch to battery. The battery just takes over seamlessly, and it's a direct connection to the inverter. It doesn't go through any DC to DC conversion. It's just a direct connection into the inverter, and the inverter changes that DC into AC and carries on going. You will not see any blip or any switching in this process whatsoever. The AC output will remain constant when you lose AC input power. Okay. And then once we get down to the battery end of discharge level, which on our systems is usually 105 volts DC for a 60 cell system, then this battery breaker here, it's actually inside the UPS, trips. And before it does that, it switches the static switch from inverter to load to bypass to load. So the bypass source will go through the static switch out to the AC output, and then this static switch will turn off, and then this breaker here will trip. And once again, notice that we don't use in an full industrial UPS, We do not use a contactor on this branch here to bypass the static switch once we've switched over. This static switch is rated to carry the full system load the whole of the time. So there isn't another point of failure when we transfer to a contactor, because contactors are obviously mechanical devices and they can fail. Static switches are semiconductor based and very, very, very rarely fail, and they switch instantaneously. And then the last thing we have is the manual bypass switch, and that allows us to bypass power around the static switch. You can see that this contact here has moved to this position, and that allows us to remove power from here, and if it's an external remote manual bypass switch, it actually allows us to remove power, and it would go outside of the UPS that way there. But it makes the UPS safe to have maintenance or repairs done on it. Okay, so that's the general theme, the basics of how a UPS works. And now we're going to mention the different topologies. In other words, it's a fancy word for saying how you can connect them together to give you some form of redundancy. So what we've talked about is a single UPS. And now in this screen here, we have what's called a dual parallel redundant UPS. Now, the important thing to remember to start off with, let's say your load design, say we needed 20 kVA of power to the load, then what you have to do is this UPS down here has to be able to supply 20 kVA. And this UPS here needs to be able to supply 20 kVA. Because when it's parallel redundant, what we want to do is if this UPS here doesn't work anymore, we want this UPS here to be able to continue and supply the full power to the load. So they have to be rated to, both UPSs have to be rated to supply power to the loads. Okay. But a normal operation, once again, we use red for power flow and green for ready if necessary. So the power flow, both UPSs are flowing power from their chargers through the inverter, through the static switch, and then they are connected physically in parallel. So if it's a single phase UPS, the hot will be connected together and the neutrals will be connected together, and then that will go out to the load circuits. And then there is internal logic inside the UPS that monitors each UPS, and it will change as load increases or decreases, as power factor increases and decreases with different loads. Then the logic will make sure that both UPSs share the load at all times. Okay, but we still have the bypass supply available just in case both UPSs fail. We still want to have a backup supply. So that bypass is sitting there just in case both UPSs fail, or you're going to do maintenance on both UPSs for some reason. Okay. Now, on an AMETEK solid-state controls UPS, and you have to check, if you have different manufacturers at your plant, you have to check what the standard design of their systems is. But on our system, if you lose AC power to one of the UPSs in a parallel system, then what's going to happen is that rectifier turns off. And once again, just like you pulling the power out of your laptop, the battery is going to carry on supplying power to the inverter. The inverter is going to remain on, and it will continue to supply power in parallel with the other UPS out to the load circuits. Okay. And then if we get to a situation where if this battery, once again, if it was 60 cells, if that got down to 105 volts DC, then this system here will, in normal operation, if it was a single system, it would try to transfer the system to bypass. But because we know that this UPS here is healthy, what it does is it switches this static switch off. and then it trips this battery breaker here to protect the batteries. And this UPS here will continue supplying the power to the load without any issues whatsoever. Your loads will not see anything happening. They will just carry on being fed by the UPS. And basically this system here is now out of action. Okay. And then in that circumstance, if both UPSs, if the same happened to both UPSs, okay, or if the inverter then failed in that UPS, then only then will the bypass supply come into action, okay? We only use bypass in a parallel redundant UPS when the output from both inverters into their static switches fail. The logic will detect it. It will immediately switch on the bypass static switch, and the loads will be powered this way. Okay, that will be off, and that will be off. So that is a parallel redundant UPS when both inverters fail. This is another design of system that we've seen gaining traction. I see some engineers speccing this out for new UPSs, and it's when the UPSs are connected with redundancy at the loads themselves. Okay, so what you have is you have two individual UPSs. Okay, let's say this is A at the bottom and this is B at the top. And you can see, let's draw this one out here. So B goes up into this power supply here, and A goes up through a distribution board into this power supply here. Then these power supplies convert the AC into DC. There's a blocking diode on the output of each system so they don't backfeed each other. And then they are paralleled at the output of this point here. So if either of the UPSs fail, A or B fail, you still have one power supply that is continuing to feed whatever the circuits are in that dual fed load. This is actually, it's a good system. It gives you really good redundancy still. It means you don't have the parallel logic. Now, we always have logic between the inverter and the bypass static switch, but these two UPSs don't have to speak to each other in this configuration. In truth, you could have a 20 kVA UPS here from one manufacturer and a 20 kVA UPS here from another manufacturer, if you wanted to. It doesn't make sense because you want all the spare parts and everything to be the same, but you could, in theory, do that. The only issue with this system here is you have to, whenever you add load onto the output of a dual redundant UPS connected at load, you have to remember that you always have to connect both UPSs to that load to add that redundancy in. And what I've seen historically is when there is a project that comes up and they say, oh, I need UPS power, then they'll look at the drawing and say, okay, let's take UPS power from the UPS A distribution board here, and they'll run it down to a different load out here. And they won't connect UPS B to that load. They'll forget about that. And then when you do that, you don't have the redundancy anymore. Yes, that load will still be backed up by a UPS, but it won't have parallel redundancy. So always be careful when you have this kind of UPS. When you're adding additional load after the systems are installed, maybe a few years from the time they were installed, you have to remember to add both feeds to that additional load that you have added. Okay. And if we have an AC input failure on UPS A, the rectifier turns off, but the battery is going to continue to supply power to the inverter, and it will supply power to all of its loads this way here. And then when that battery depletes and gets down to 105 volts, the charger turns off. Okay. And this logic here is going to say, okay, wait a minute. Our inverter has failed, so that means I need to transfer to bypass. Bypass will come down through this static switch, and we will continue to feed bypass into these loads, and inverter B will continue to feed backed up power into the other loads. So it's quite a robust system. And it is gaining some traction, but once again, you have to work out the cost of the additional cabling, running dual cables to each of the loads, all that kind of stuff, and all of the loads that you have to have the ability to accept 2 AC power sources when you do that as well. And then another topology that we see very frequently is what's called a Cascade UPS. And once again, we'll call this UPS B and we'll call this UPS A. So once again, red is normal power flow. So in a Cascade UPS, the primary UPS, which is UPS A, will feed power and all the power to the critical loads. The B UPS will keep its battery charged. The inverter will be on, but the static switch here is not on. Okay, it's waiting for a signal, because basically what's happening is UPS B is acting as the bypass supply for UPS A. Okay, now once again, if we have a primary power fail, the rectifier turns off, the battery continues to supply power to the inverter into the static switch and out to the loads. Okay, the loads will not see that. As I've mentioned before, it's just as if nothing happened. The outputs 120 volts will be seamless and not see any effect from that loss of power on the primary AC supply. And then only when the battery gets down to 105 volts DC, the battery gets disconnected, this static switch has a logic signal that says, okay, when we switch this static switch on, this static switch turns off, and UPS B now starts supplying the load. And remember, UPS B has its own battery, so we still have full UPS backup for the loads in this circumstance. And then only when UPS B fails as well, so A has failed, B has failed, only then would we then supply power through the bypass static switch from UPS B. Personally, I like Cascade UPS design. They're very flexible. There is no complicated logic between the two UPSs. And once again, you could have, for UPS A, it could be one manufacturer. And for UPS B, it could be a completely different manufacturer, a second manufacturer. There is no electronic communications between the two systems in a Cascade system. So you could have an AMETEK UPS as one, and you could have an old different type UPS in the other. It doesn't matter. Once again, it doesn't help when it comes to your spare parts. You would want to have two systems identical, so spare parts work in both systems, but in truth, you can have two different systems that allows you a little bit of flexibility. And then we're going to discuss the bypass switch. So the bypass switches usually have three positions. So N is normal, BTL is bypass to load, and BI is bypass isolate or isolated bypass. Okay. Now remember, so here's the switch here. Here's one set of contacts on the switch here, and here's one set of contacts on the switch here. The other set, sorry. Okay, so they are drawn here, two sets of contacts. Now remember, this is the mechanical switch. So in this circumstance, this is usually a rotating switch. You move it from normal position to bypass to load, and then from bypass to load to bypass isolate. So it is an actual mechanical switch that does have moving parts. The contacts are designed to be make before break. So when you move from one position to the next, it does give you a seamless transfer without any break in supply. But it is mechanical. So there is the opportunity for the contacts to fail at some point, but they're usually very robust. So in normal operation, with the bypass switch in the normal position, power will flow from the UPS through this normal contact here and out to the load. And you can see we also have this normal contact here. So bypass supply is allowed to flow through and is ready at the static switch, but this static switch is off because it's not required at this time. Okay. The next position is bypass to load. And you can see the power flow now. On this contact here, we have now moved to this position. So we are no longer going from normal to this point here. So now at this point, the UPS is not feeding the load. Bypass is now going out here, along here, down here through this bypass to load switch, out through the loads. But you can see that bypass still goes through the static switch. And that's important because there has to be a period where you have to have the static switch on bypass before you move the mechanical switch to bypass to load. And then the final position is bypass isolate. Let me just move it, this one here. And now you can see power flows out through here, through the bypass isolate contact. So now it's not this contact, the bypass to load, it's not the normal contact. And you can now see here that there is now no power going into this static switch. So what that would allow you to do is have the primary AC power off. You could disconnect the battery and you could move the system into bypass isolate, and there is no power at the static switch or at the inverter or at the rectifier. And you could work on this system safely. And just for interest, this is how an external RMBS is connected with our UPS systems. So this section here is an AMETEK SCI UPS. This section here is an AMETEK RMBS. So this is the RMBS. Excuse my handwriting with this pen, and this is the UPS. So there are two individual pieces of equipment, but they are designed to be connected together. You can see here that terminal 110 connects to terminal 110 inside the UPS. The neutral is 15. So now this is from your MCC, okay? And it's going to be 120 volts. This is your bypass supply. And now what happens is the bypass is going to go in here and it's going to be available at the static switch, okay? And then the output of the UPS is wire 199. That connects to wire 199 in the MBS. And power from the output of the UPS is going to go through the RMBS and out to your load this way, okay? So power is going to go out that way, okay? Ooh. And then what happens is if we move this RMBS to the bypass position, then what's going to happen is that is going to open, but before that opens, this closes, and it allows bypass power to go down through that switch out that way there, and then it will then open this contact and the UPS is no longer supplying power. So then what you can do is move the switch to the bypass isolated position. That will then open that contact, and then there's no power on these terminals. There's no power on these terminals. You can switch off the AC input there. You can disconnect the battery here, and this UPS, in truth, what you could do is disconnect all the cables. You could remove that UPS from service, and you could install a brand new UPS while the loads are still powered from your bypass source. So you don't have to take an outage if you have a system with an RMBS when you're replacing the UPS, and it also allows this system to be completely volt free to allow maintenance to be performed. So now we're going to discuss some common misconceptions. I'm just going to take a drink while you take in Albert Einstein's famous quote. Now, misconceptions, like Einstein says, anyone who's never made a mistake has never tried anything new. So if you have one of these misconceptions, don't beat yourself up about it. It just means it is something that somebody taught you or something you learned by mistake from somebody else that just needs to be corrected and thought about a little bit more. Hopefully that explains things. And the first thing is, for an industrial UPS, most people say, well, I need a three-phase 208 volts output UPS. Now, in most cases, not in all cases, but in most cases, there is never a 208 volt load connected to a UPS, okay? It is usually always a 120 volt system. The 208 will go into an AC panel, and those AC panels will be split to 120 volts to neutral supplies that then go out to the loads, okay? You have to remember that a 208 UPS will not clear a fault on the output as good as a single phase UPS is, and it's down to simple math. So a 10 kVA three-phase 208 system can only supply 28 amps per phase, because that's the math. It's 28 times 3 times 120, and that gets you 10 kVA. Okay, but for a 10 kVA system, it's 120 volts times 83 amps gets you 10 kVA. So you can get 83 amps of power from a single phase system and 28 amps of power from a three-phase system. And that's important when you look at the fault current tripping capabilities of some circuit breakers that are out there. Okay, so this table here shows you time on this axis and multiples of rated current on this axis, here. So let's say this is a 10 amp breaker. Okay, it's saying that 3 times the rated current isn't going to trip until about 3 seconds. Okay, if that makes sense. So you're going to have 3 seconds before that breaker trips. So the voltage of the UPS could be pulled down on a single phase system. You remember a single phase system said 28 amps? Well, this is 30 amps. Okay, so it's going to take at least 3 to 4 seconds to trip that breaker. Now, if you had much higher current, it would trip much, much faster. So if we had, if we could supply 8 times the current, it's saying here that it's going to trip in 0.01 amps. Actually, tell a lie. I was confused about this. This point here is 30 amps, but 28, yeah, actually in truth, 28 amps does go up there, and it would trip at that point there. So yeah, it's only when you get to 30 amps that it will then trip at 0.02 seconds. But the single phase UPS that can supply 83 amps, that's will be around about here. So it's going to trip in 0.01 seconds. Okay, so it's going to trip that breaker pretty much instantaneously, and therefore all of the other loads connected to the system are not going to see a disruption in the time that it takes for that three-phase system to actually trip that breaker. Because remember, if you have a short on one system, the only way the inverter can handle that is it will try and reduce its output voltage to limit the current into that fault. And in doing so, reducing its voltage could disrupt some of the other loads on that circuit. In truth, it should trip to bypass and then clear the fault that way. But you would much rather the inverter tripped it without tripping to bypass if necessary. The next misconception is a 10 kVA UPS will give you 10 kilowatts of power. Once again, that's not correct. Most UPS systems, industrial UPS systems, are rated at 0.8 power factor. Now, AMETEK does offer UPS design that are unity power factor, but the standard offering that we have is 0.8 power factor. That means a 10 kVA UPS will only give you 8 kilowatts of real power. So if you connected a purely resistive load bank to a 10 kVA UPS, you will only be able to get 8 kilowatts of power before the UPS says, okay, that's now going above my limitations and I'm going to do something to reduce that current. And once again, what it does is it reduces the output voltage to reduce the current. So you can only get 8 kilowatts of true power from the UPS. That's because most loads historically connected to a UPS include power supplies and other things that have inductance and capacitance, and that decreases the power factor to around about 0.8. So UPS manufacturers have just stuck with that value, and that is what we offer. But once again, we do sell UPSs that have unity power factor if you need them. The next misconception is we lost power to the AC input of the UPS. Why didn't we switch to bypass? And this is a very, very common question because they're saying, okay, I've lost power to the AC input to the charger, but rather than go on batteries, if we still have bypass power available, why don't we switch to bypass? So you've got to remember, the AC input to the UPS is nearly always fed by the same main HV bus back in an MCC somewhere, okay? If the MCC that feeds the AC input has tripped, then the plant will usually be in an unstable situation. So if you've lost a whole MCC, something bad has gone on, and the plant is going to start doing things, tripping things, and putting them in a safe mode of operation. And while all those tripping functions and changes are going on, the AC voltage and frequency are going to start moving all over the place. And it may mean that the bypass within the plant, even though it's fed from another MCC, is being subjected to large pump stopping and starting that can also cause voltage dips on the bypass. So if we transfer to bypass, those dips and blips could cause load circuits to operate erratically. And we don't want that, okay? And here's a block diagram of what that looks like. So let's say MCC1 has gone completely down, okay? And that's what feeds the AC input into the UPS, okay? If MCC1 has gone down, MCC2 is still healthy, okay? But the plant is going to start putting things into safe modes of operation. And you can see here that even MCC3 is connected to the same HV bus. So if we start turning off pumps here, and we do a lot of different things, then this voltage at the MCC2 could look like this for a short period of time while the plant stabilizes because of MCC1 failing. And if we transferred to bypass, that voltage would be seen on the load circuits there, okay? But if we just went over to battery operation, then this inverter does not care what the rest of the world out here is doing. It's going to take this battery voltage here and convert it to an absolutely perfect 120 volt sinusoidal waveform that looks like this, and will continue to do so until the battery depletes. And that is down to how long the designer of the system designed the battery. It could be anywhere between 1 to 3 hours for most process control UPSs. Okay. But it is not going to be affected at all by all the disruption that's going in the plant. So these loads here are going to get a beautiful sine wave and carry on regardless when the plant is in such an unstable state. Another misconception we hear quite frequently is the battery breaker on the UPS is tripped. Do I have a bad battery? And you have to understand that not all, the majority of UPS manufacturers have a battery disconnect level to protect the batteries from over discharge. And this is specifically for lead acid batteries more than anything, because battery manufacturers specify the rating of the battery to a specific end voltage. And I've used as an example here the Enesis 3CC9, which is a wet cell lead acid battery. It will give you 200 ampere hours at the C8 rating, so 200 ampere hours for 8 hours down to 1.75 volts per cell. Okay, this means that the battery will give you a total of 200 amps for 8 hours to an end voltage of 1.75, which means you have to divide that 200 amps by the 8 hours, and you will get 25 amps per hour for 8 hours until the battery will then, by design, go down to about 1.75 volts per cell. So that's the first thing you need to understand. The second thing is the battery manufacturers recommend that a lead acid cell should never be discharged past 1.6 volts per cell, because it can lead to damage that cannot be reversed, and that's due to sulfation of the plates. The crystals will form in such a way when you go below 1.6 volts per cell that it's sometimes difficult to dislodge those crystals from the plate, the sulfation crystals, and it leads to premature failure of the battery. Okay, so the only way to protect that battery from over discharge is for the UPS to prevent the battery going below this voltage, and therefore AMETEK SCI have a trip function on the battery input breaker that is set at 1.75 times the number of cells. Now, in most circumstances, for a 120 volt nominal DC system, that is going to be 60 cells. And if you multiply 60 by 1.75, you get a total of 105 volts. And that's the voltage that I've been mentioning in the previous slides throughout the presentation. So when the DC bus gets to 105 volts per cell, the AMETEK SCI UPS will transfer the system to bypass, and then it will trip the battery input breaker to prevent the batteries from going below this 1.6 volts per cell, which can cause irreparable damage to the battery. And the batteries are very expensive, so we want to protect them from being over discharged and needing replaced. And I think this is the last misconception. We had a fault on a load circuit and the UPS transferred to bypass. Why did it do that? So inverters have devices in them that must be protected from overcurrent. So the way that the UPS switches the DC back into AC is using what's called an IGBT, which is an insulated gate bipolar transistor. And those transistors are very, very sensitive to high current situations. They will basically blow up if too much current flows through them. So if we buy a 100 amp IGBT, we want to make sure that the current doesn't go above 100 amps through that IGBT. So for a 10 kVA UPS, the output current that we say out of the system at 0.8 power factor is 83 amps. So at a certain point after the 83 amps is reached, the system will go into current limit to protect the IGBTs. Okay, the system is saying, okay, we probably just for ease, we'll say in this 10 kVA UPS, we'll say 100 amp IGBTs were used. So we want to make sure that anything above 83 amps, we start limiting the current, because we don't want to get close to this 100 amps that could blow up an IGBT. And the only way to limit current is simply by reducing the voltage of the system to maintain a current at a certain level. And it's all down to Ohm's law. So the output current of the output resistance, of the system, if we have 83 amps of current, is 1.44 ohms. So it's basically, Ohm's law says current is equal to volts divided by amps. So it's 120 volts divided by 83 amps. So that means the resistance of the load must be 1.44 ohms. Now it's important to understand, if the load increases, the resistance decreases. So if we went down to a 1 ohm load, in other words, more load was added, then Ohm's law says we're now going to draw 120 amps. And that's too high. That's going to blow up the IGBTs. So the only way that we can protect the IGBTs is to reduce the voltage out of the system to reduce the current. So remember, volts is equal to amps times resistance. So therefore, we would have to reduce the volts to 83 amps times the resistance, which is 83 volts. Now, in most circumstances, that is going to be too low for the loads to stay good. So we will have the static switch will monitor this voltage, and if it sees it go that low, it will usually cause the system to transfer to bypass. But the main reason it does all of this is to protect the IGBTs, those 100 amp IGBTs that I mentioned. That's what we're trying to protect. So it will do everything it can to stay on inverter and keep the voltage up. But when Ohm's law says it has to go past, let's say, 100 volts AC, the system is going to say, that's too low for my loads. I'm going to transfer to bypass. Okay. And that's basically showing you in block diagram level what happens. If there is too high a current going through the IGBTs, then the system is going to transfer to bypass, and then the bypass will clear the loads. The bypass has a huge amount of power behind it, and it will trip the load if necessary to clear that fault. And then if the system has auto retransfer turned on, then it will switch back to inverter once that fault has cleared. Oh, we still have one more. Okay. All the PCBs should be plug and play. A very common misconception. What you've got to understand is every PCB has many, many different analog components on them. Okay. Resistors, capacitors, and that all goes into usually an analog to digital converter. Okay. And the resistors have tolerances. They're not perfect, and we cannot guarantee that a 10 ohm resistor is exactly 10 ohms. So when we're setting the boards up and monitoring things, those tolerances in the resistors are going to be different for every single board. So we have to have a way to calibrate each and every individual board for the system that it is installed in. So that means every board can't be plug and play because it has to be calibrated. Okay. And to do that, you have to go through a special engineering password protected menu system, because we can't allow our customers into that menu system, because there are so many things that you can change that if you just change one digit accidentally, it could cause your system to blow up and be really in a bad situation. So we always have it so that it's a password protected area where we can go in and calibrate those systems for you. I think we've now changed it so you can calibrate some things from the screen in the latest versions of what we have done. But historically, it's always been in a password protected system. And the reason why we do that is because R&D are continuously looking for obsolescence. And like since COVID, we've had to replace our processor on the control board about 3 times, I think it is. So sometimes when you change the processor, you have to change the way that the boards actually work a little bit. So you do need an AMETEK SCI field service representative to go in and replace that board because of the mismatch in the processors. So there's a lot of complications when it comes to control boards. We wish we could just send out all control boards and they'd be plug and play, but it's not quite as easy as everybody anticipates. I'm going to skip this one today because we're getting close to 11 o'clock. And that one there. Okay, we're going to get to the end here. There's too many things here. There are in that last section there, that is in another one of the videos that we've had previously. But I just wanted to get to 11 o'clock and give people some opportunities to ask some questions. So let me go to the Q&A section. Why did the dual-fed load configuration have an additional rectifier? Okay, very good question. It's because in near enough all circumstances in a UPS, the loads that most UPSs feed are control systems, and whether that be a DCS system, a video screen, a control room, something like that. And those additional rectifiers are inside the DCS equipment themselves. So the UPS feeds AC power into that DCS system, but that DCS system accepts that power and then changes it back to DC. I know it sounds silly, but that's what they do. So that's why the additional the dual fed load configuration had additional rectifiers, because built into, let's say you buy a Delta V system. The Delta V systems are now designed where they have actually 3 inputs. You can put UPS A into the back of the DCS system. You can put UPS B into another plug in the back of the DCS system. And then you can take another grid powered supply that's not UPS protected from a different MCC and plug it into the 3rd connection. All those 3 connections go into a power supply that then converts that AC back into DC. Okay. And then because you can't, it's very difficult to parallel AC circuits. Paralleling DC circuits is very, very easy. So that's why we do it at the power supplies. Hopefully that explains your question, Ravneet. Another question is, I'm looking into a 600 volt 3-phase to 240 volt single phase UPS. Would the 240 volt single phase power be phased to ground or phased to neutral? It would never be phased to ground. Let me answer that question first. And that's a very common misconception. We never ever connect anything to ground. That is based on your grounding design at your plant itself. Okay. Now, yes, you will connect the neutral to ground somewhere in your system if it is a neutral grounded system. In other words, it's not a high resistance ground circuit. But you have to realize that the UPS is classed as a separately derived source, so that should only be done at the bypass transformer neutral down to ground. So we should never say you connect 240 volts single phase to ground. It will always be single phase to neutral or phase to phase. And that basically depends on what you order. For us, a 240 volt single phase system would always be 240 volts phase to neutral. It's basically the European and the Middle Eastern standard is 240 volts, although we see some where it's a split phase system. But once again, it's down to the specifications when the UPS is ordered. If you specify that you want 240 volts AC as a single phase supply, it will 9 times out of 10 be phase to neutral. And then we have another, what happens if energizing a transformer on the UPS load side? Does the UPS see inrush as load fault and static switch to bypass? It's a very, very good question. Very good question. And in some circumstances, yes, a transformer on the output of the system, if you close that transformer in when the UPS is running, the UPS could see the inrush to that transformer as a fault current. Because let's say, for example, you have a 10 kVA UPS, and I'm using that because we know it's 83 amps on a single phase system. And if you have a 10 kVA transformer, the inrush current to that transformer could be 5 times the nominal current. So that could be 400 amps. Okay, as we described, the UPS is going to protect its IGBTs from seeing that 400 amps. So yes, it will transfer to bypass. And then once that transformer is energized, you can transfer the system back to inverter, and everything will be okay. So it's not a design fault. So the proper way to energize that load transformer, I suppose the proper way would be to switch the UPS to static bypass, energize the transformer, and then turn the UPS onto static inverter. Oh, for some reason, my computer has locked out. Hopefully you can still see. Yeah, there we are. Phew, never done that before. So hopefully that explained your question, Chapman. It was a very, very good question. Very good indeed. Another question, does AMETEK provide integrated BMS, battery monitoring systems that estimates battery hours left? Yes, we do. The DPP UPS does have a battery time remaining option. We have to know what type of battery it is, what ampere hour the battery is, and all those kind of things at the design stage. And then, yes, our UPS does have an integrated battery hours left function. Some very, very good questions. I did see a question in the chat bar as well. Can you feed one UPS to another UPS on the maintenance bypass terminal? Yes, that is called a Cascade UPS. Okay, that's for Meshach. That is what I mentioned, Cascade. You feed one UPS, that would be UPS B, would feed into the static switch bypass terminal on the UPS A. Okay. Okay, if there's no more questions coming in, sorry, once again, I'm 10 minutes over time. I knew this one would take longer than necessary because I do speak a lot about UPSs. If you have any questions and you need to contact SCI, London is going to put our contact details in the chat bar. And once again, our presentations are not provided, but you can rewatch the session. Our PDFs and our presentations are proprietary, but our videos are absolutely fine for you to share, and you can go to our YouTube channel that is in the chat bar there. And if you have any questions, you can contact the website that London just posted. You can contact our email address, which is sci.marketing@ametek.com. Or if you want to be old-fashioned, you can call our number and speak to a human. So at 1-800-635-7300. So hopefully you learned some stuff. Hopefully I didn't talk too much, which I have a tendency to do, unfortunately. UPSs are my life, so I do tend to talk about them too much. And one last thing, if you have any suggestions whatsoever about next month's webinar, please take 2 minutes to complete our survey. I think it's question 5 asks, which topic would you like us to cover at the next webinar? I do read every single one of those surveys because I'm looking for things that people want me to talk about, and that's why I did it this month. People were asking about a basic UPS overview again, so I did it again. So if I see something in the surveys that come back to let me know you want to talk about static switches in more detail or semiconductor devices in more detail, then I'll tailor the next webinar to focus on that. So without any more questions coming in, thank you for hanging around for an hour and 10 minutes to listen to me talk. I really do appreciate it. I know that you have busy days, and for you to take time out of your day and listen to me is greatly appreciated. I hope you learned something, and I hope you come back and watch our video next month. So until then, take care. Thanks for watching and enjoy the rest of your week. Thank you.